Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe.
The James Webb Space Telescope has made a remarkable discovery. It found that some of the earliest galaxies were much brighter and heavier than we expected, based on our current understanding of the cosmos. But how did these galaxies become so luminous and massive in such a short span of time? And what does this mean for our understanding of galaxy formation and evolution?
In a new study, astronomers used JWST to observe 6 galaxies that shouldn't really exist. You see, we thought that right after the Big Bang, galaxies would have to be tiny, right?
To uncover the mysteries of these early galaxies, the first step is to locate them and measure their characteristics. This task is far from simple because these galaxies are both distant and faint. Their light has traveled across the universe and been stretched into the infrared part of the spectrum. Scientists used a specialized tool on the JWST called the Near Infrared Camera, or NIR-CAM, for this mission. NIR-CAM is designed to capture images of the infrared sky with incredible sensitivity and resolution. It also has filters that can isolate specific wavelengths of light related to different aspects of galaxies, like hydrogen emission lines or stellar populations. Using these filters, scientists can estimate important information about these ancient galaxies, such as their distance, size, mass, brightness, and rate of star formation. However, one question remains. How do we know which galaxies belong to the cosmic dawn, a period occurring about 540 to 770 million years after the Big Bang? The answer lies in something called redshift. Redshift is a measurement of how much a galaxy's light has been stretched as the universe expands. The higher the redshift, the older and further away the galaxy is. For example, if a galaxy has a redshift of 10, it means we are seeing it as it was when the universe was only about 500 million years old. Armed with the capabilities of NIR-CAM, scientists started their quest to search for galaxies with redshifts between 9 and 12, which are believed to be from the cosmic dawn epoch. Using this approach, they identified 14 candidate galaxies from the cosmic dawn. These galaxies earned the name JWST, Early Release Science Galaxies, or simply JERGs. What makes these galaxies particularly intriguing is their exceptional brightness and mass for their age. Their luminosities are extraordinary, ranging from 10 to 100 times that of our Milky Way. Similarly, their masses are strikingly high, varying from 10 billion to 100 billion times the mass of our Sun. These findings have challenged the standard model of cosmology, which assumes that galaxies evolve slowly over time by merging with smaller ones. So, how did these early galaxies become so incredibly luminous and heavy in such a short time frame? The key to understanding this enigma may lie in something called cosmic feedback. Cosmic feedback refers to the exchange of energy and matter between galaxies and their surroundings. It's a bit like a cosmic give and take. These ancient galaxies may have experienced intense bursts of star formation, resulting in the formation of massive stars. These massive stars, in turn, emitted powerful energy in the form of light and stellar winds. This energy could have triggered a chain reaction, impacting the interstellar medium and even neighboring galaxies. The release of this energy could have played a crucial role in making these early galaxies extraordinarily luminous. It's as if these galaxies were briefly ablaze with cosmic fireworks, shining far brighter than we could have predicted. Furthermore, the high masses of these ancient galaxies could be linked to a process known as cold flows. Cold flows are streams of gas that flow into galaxies from the cosmic web, the vast structure of the universe. These gas flows might have deposited large amounts of matter into these galaxies, rapidly increasing their mass. This revelation challenges our current understanding of how galaxies evolve over time. The standard model of cosmology may need some revision to account for these unexpected findings. Until now, what was our understanding? We believed that galaxies grew slowly by merging with smaller galaxies over billions of years. However, the JWST's discovery suggests that there might be more dynamic processes at play. These galaxies seem to have evolved rapidly, defying the conventional wisdom of a gradual cosmic assembly. This not only expands our knowledge of galaxy formation, but also opens up exciting possibilities for future research. To uncover the secrets of these early galaxies, scientists used the Blue Tides computer simulation. This extensive cosmological simulation represents a virtual universe spanning 400 billion light-years. It can simulate how dark matter, gas, stars, black holes, and radiation interact in the early universe, shaping galaxy formation and evolution. Comparing the simulated galaxies with those observed by JWST, scientists unveiled a fascinating explanation for the exceptional brightness and mass of these early galaxies. They discovered that these galaxies were not as large and stable as they appeared. Instead, they were small and bright due to bursts of star formation. These galaxies experienced intense star formation episodes lasting millions of years. During these bursts, they generated thousands or even millions of new stars annually. These stars emitted intense ultraviolet radiation, which ionized surrounding gas, making it glow in infrared wavelengths. This radiant glow made these galaxies appear larger and brighter than they actually were. This discovery challenges the standard cosmological model, which assumes slow, steady star formation in the early universe due to feedback mechanisms. However, in the cosmic dawn epoch, these mechanisms were less effective, with rare supernovae and smaller black holes allowing for rapid, chaotic star formation and creating these incredibly bright, massive galaxies in a short time. Let's see how these early galaxies compare with others seen by the James Webb Space Telescope, JWST. Galaxies can be compared by their infrared colors, revealing temperature and dust content. Blue hues indicate very hot, dust-free galaxies, while red signifies cooler, dustier ones. The jugs are remarkably blue, signifying their high heat and lack of dust, which aligns with their high star formation rates and low metal content. However, the brightness and resolution of the jugs might be misleading. They could actually be smaller and clumpier than they seem. Another way to compare is by studying galaxy sizes and shapes, reflecting their structure. Large, round galaxies have smooth profiles, while smaller, irregular ones have clumpy profiles. The jugs display smooth profiles, suggesting they are large and round. But this might be due to the jerg's extreme brightness and the limitations of Webb's NIR cam, which can't distinguish smaller objects. In contrast, other galaxies observed by Webb are red and dusty, indicating they are cooler and dustier. These galaxies likely formed earlier, enduring more feedback from supernovae and black holes, accumulating metals and dust. They may be more massive and stable, possibly hosting larger black holes. What do you think of this massive revelation? Do you think our current understanding of the origin of our universe is flawed, and we might be inching closer to debunking the Big Bang Theory? Let us know in the comments below.